hash table work, right? What is a hash table? Hash table is what? It's an array, right? It's an array of values. So I take a value in, I crunch it through the hash table, an integer pops out, and then I use that integer as an address into the array for the location where I'm going to store that particular value, right? That's how a hash table works. What properties does a hash function have? There are certain properties that a hash function needs in order to be effective. Does anybody know what some of those properties are? Yeah. It's got to be repeatable. So if I put the same value in twice, I need to get the same value out twice, right? I have to be able to get the same value out twice. That's really one of the most important features. There are a couple of other ones that are worth talking about too, though. Anybody remember other features of hash functions? Yeah. It has to use every piece of the inputs. I'm not actually certain that that is a requirement. I think that's a nice to have. I'm not sure that's a need to have, though, necessarily. Yeah. Can we think of some need to haves that a hash function needs to do for us? What does a hash function absolutely need to do? Yeah. Yeah, there we go. That was one of the things I was looking for. The integer value that it gives back is important because we're using that integer as a value into an array, right? So that integer has to be in the range of whatever array I'm using in this particular case. And ideally, it would be somewhat relatively distributed across the array so that everything's not getting all lumped into the same location. The easiest hash function in the world is to just create a function that returns 0 every time. That's a hash function, right? It's repeatable. I give you you give me a value, I give you 0. You give me that same value, I still give you 0. Not a very good hash function, though, because everything is going to get dumped into the same location. So that's not good. Speaking of that, so we stated that a hash function is an array of stuff, and a hash table, I'm sorry, is an array of stuff, and I use the hash function to decide where that stuff goes. What happens if the hash function tells me to put more than one thing in the same location? What do I do then? What's that called? It's called a collision, right? It's called a collision. So what do I do when that happens? How do I get around that? It seems like a problem to me. It seems something I'm not too happy about. How do I fix it? Yeah. Linear probing. Okay. Yeah, so I can if the address that I want is occupied, I can just keep looking next door until I find one that's not occupied, right? But even that, eventually, I'll run out of space. So then what? I fill the whole thing up potentially, right? And now I have no other spots left to do. Now what do I do? Yeah. You can do chaining. So what's chaining? Yeah, so we can use linked lists to help us resolve collisions. So now if I have two things that point to the same location through my hash function, what ends up happening? What does that look like in our hash table? I go to that location, right? I see a pointer. What's that pointer pointing to? One of those values, right? If I have multiple values, it's pointing to one of those values, and then that value is going to point to the next one. It's a linked list, right? It's just a linked list structure, which is what we talked about last time. And another reason why we're going to talk about linked lists even more today, because they play a very important role with hash tables. Yeah, so I guess that sort of covers how we insert values into a hash table. We run it through the hash function, and that tells us what location it goes into. How do we get stuff out of a hash table? I say, go find me this value, please, or tell me if you have that value, please. What do you do? How does that work? How do I find it? Yeah. Yeah, exactly. So I run it through the hash function again. The hash function is going to give me the same value, right? Every time, as long as I give it the same input every time. So it'll tell me where that thing should be. And if I go there and I don't see it, well, that's not necessarily a problem, right? Because it could just be a linked, farther down the linked list. I might just have to go through and search for it in the linked list. And we talked about how to do stuff like that last time with linked lists, how to iterate through lists. Cool. So then let's talk about efficiency. What's the efficiency of putting values into a hash table? Best case efficiency, putting values into a hash table. Big O of what? Big O of what? Yeah, you got it. It's constant. It's constant time. It's going to take the same amount of time no matter what the value is, right? Well, that's the best case scenario. What is the best case scenario assuming? There's a big assumption that goes along with that best case scenario. I do get constant time, but only if one particular condition is true. No values in the list or no collisions, right? I don't have any values that want to share the same spot. So if every spot has exactly one value in it, then that's the best case scenario. It's constant time to put something into the hash table, right? What's the worst case then, with that in mind? What's the absolute worst case for putting something into a hash table? What would be the absolute worst case? I look at the hash table and what do I see? Am I going to see one value per spot? That's our best case. So if that's our best case, what's our worst case? We don't like collisions, right? So our worst case is everything collides with each other. Our worst case is that hypothetical hash function that always returns 0. We're just going to stash everything in one bucket, right? Like you did when your mom told you to clean your room as a kid. You just shove it all in the closet. Just get it out of the way. Shove it all in there. So now if we want to find stuff, what do we have to do? We have to go to that location and we have to search through the whole thing potentially. And if it's all the way at the very end of the list, that's the absolute worst case, right? Everything's all in one giant list. It essentially becomes a linked list at that point. Do you see how that works? It essentially is a linked list. In the worst case scenario, we have a linked list. So finding something in a linked list is big O of what? N. Big O of N, where N is number of things in the hash table or in the list in this case. Oh yeah, did I say finding? Well, inserting, I guess. Oops. What's the best case scenario for looking something up in a hash table? Best case scenario. It is. Did I hear somebody say? I can't hear. Sorry. If it's well, so where it is in the list is very much irrelevant because the hash function is going to. Oh well, I'm sorry. I understand what you're saying. First thing in the linked list. Yes, I understand now. So that's the best case scenario. So what is that? Big O. I heard somebody over here say it. Constant time. Yeah. Best case scenario for hash tables, putting stuff in and getting stuff out is constant time. Worst case scenario for hash tables for putting stuff in and getting stuff out is O to the N, where N is the number of things in the hash table. So yeah, just remember, best case scenario, we've got a nice array with one value per element. Worst case scenario, we have a linked list. We have to search the entire linked list to find what we want. Any questions about hash tables? We'll talk about hash tables perhaps a little bit more later on. Any questions right now? No? A couple final notes on hash functions. You have a choice when it comes to pset5. They give you an option as to what data structure you want to use. They suggest 2 data structures. One is the hash table. The other is, I think, what we're going to talk about next, which is a trie. It's ultimately your decision. You get to pick which one you want. However, if you ask me, I would recommend hash tables. So just keep that in mind. Hash tables are by far the more useful of the 2 in general. I think a trie is a pretty neat solution to this pset, and I don't want to discourage people from implementing it using a trie. You can get some really cool solutions that way. But a hash table in general is the much more useful data structure of the two. So just keep that in mind when you start to work on P-Set 5. Let's talk about tries. What is a try? Can somebody explain a try to me? How does that look? I go to a try. What am I going to see? What am I going to see when I look at a try? Yeah. An array of pointers. Yes, that's exactly right. But wait a second. Didn't we just say a hash table was also an array of pointers? So what's the difference? What's the difference? The structure's a little bit different. Yeah, is that your hand? It points to another array of pointers. That's exactly right. That's exactly right. It points to another array of pointers. So if I'm putting in, if you watch the videos for try, they talk directly about spell checker, right? Each array is containing pointers to other things, but it also contains something else, right? Or the way the pointers work is based on what exactly? How do I know what's being stored in a try? How does that work? I start with the first array, and then what am I looking for? I'm looking for possibly a bool or a key, right? So for the case of spell checker, I have words. I'm checking words. So I look at that first array, and what am I going to do with that first array? I have the first array, and I have my word. What am I going to do? I'm going to check the first letter. So I'm going to go to the array, and I'm going to look up the first letter. So there's 26 letters in the alphabet. The first letter is D. I'm going to go to position number 3, right? Because we start with 0. And look at see what's there, and hopefully I see what? A pointer that's pointing off to what? Another array of nodes. And so then I look at my second letter, right? Maybe I'm doing the word dog or something. So I take that letter O, the second letter, and I plug that into the second array of nodes, right? And then hopefully I see that that value is there, and then I go do the same thing for the third letter. But when I get to the last letter, the third letter in this case, the G in dog, what do I expect to see? How do I indicate that that's actually a word, that's actually something that I found that's useful? I have to have some way of indicating that this is actually an entry and not just a series of gibberish letters. Does that make sense? Yeah. Yeah. We have a Boolean on the very last character to indicate that that is a word that we care about. That is a word that we know about, right? That is a valid word. So tries are some similarities to hash functions. We've got arrays of pointers, but also kind of different. So when it goes to insert things into a try, we use the same example with D. How do I insert that into the try? The first thing I'm going to do is I'm going to go look up, position number 4 in that list of pointers. Position number 4. Position number 3, because we start with 0, in that list of pointers. And what am I going to do? I either see a pointer or I don't. If I don't see a node pointer there, what do I do? What do I have to do? I have to create one, right? And that means I have to malloc a whole other array of stuff for that pointer to point at, right? I have to malloc a whole other set of a whole other array of node pointers. So I malloc that, right? I set up the D pointer to point at that new array. Then I go do the same thing with O. If I already see a pointer there, then I'm good. I just follow the pointer. If I don't see a pointer, I have to malloc it and create another array with pointers in it, right? And then I do the same thing for G, malloc the final one if I have to. Make sure to set that Boolean to true to indicate that I created a word, inserted that word into the try. And then we're done. We finished with the insertion process. And so finding things, I kind of already walked through that example, right? Check the first node pointer, hopefully it exists. Check the second node pointer, hopefully that exists. Check the next one until you get to the last character, and then you hopefully see that Boolean marked as true. If it is, then the word's there. If it's not, then the word is not there. Does that make sense? Are there any questions? Any questions? So let's talk about efficiency with a try. big O notation again, right? If I want to put something into a try, what's big O of that? This is in the lecture notes for this week. I know, because I just double-checked it right before class. It's big O for putting something into a try. It's constant. Yeah, it's constant. It's a little bit hard to wrap your brain around perhaps why it's constant. But consider that when I put a word in, it doesn't really depend at all on what other words are in there, right? The fact that there are other words in the try does not affect really how fast or slow it takes me to put that new word in the try, right? It's the same process, whether it contains other words or whether it's empty. It's the same process. So what's then the worst case scenario of putting something into a try? That's the best case. What's the worst case? It's also constant, yeah. So it's kind of got a leg up on a hash table in that regard. Worst case for a hash table is big O to the n. Worst case for a try is constant. Best case for a try is constant. What about finding something? What's the best case of finding something in a try? It's also constant. Everything with a try is constant. Constant lookup, constant insert, right? That makes it sound a lot better than a hash table. Hash table has a worst case scenario than a try does. Yet I stand by my assertion that I like hash tables better than tries. Can anybody think of a downside why tries are potentially worse than hash tables? What the issue might be? I'm sorry? Yeah, a lot of space. They're huge. I'm creating a new array of pointers every time I see a new letter, right? So if I have, a very large dictionary with lots of words in it, that's going to be a ton of arrays, right? A lot of space being taken up. So you have to be really careful if you do decide to use a try when you do your mallocs and your frees, because that's a lot of memory that you're taking up. That's a lot of space. The benefit that you get from it is very efficient structure, very fast lookup time, very fast insertion time. So that's the trade-off there. There's always a trade-off, Hash tables, perhaps a little bit worse in the worst case, but a lot less space, a lot less memory. Any questions about tries or hash tables? So again, you do have a choice between the two when it comes to spell checker. I'm hoping that some of you might try and do both. Because if you haven't taken a look at Pseudocode already, one of the things that they have you do is they have you time it. They actually have you time your implementation. How long does it take you to spell check all of these words in this particular file? And one of the things that you might notice if you do get around to implementing both versions is that certain structures might give you faster implementations than others, right? That's to be expected. That's a good thing. And part of a programmer is understanding when that's going to happen and being able to choose the right structure for the job, being able to choose the right data structure for the job at hand. Okay. There was one other data structure that they talked about in the prep work for today's class, but it's not a part of P-Set5. I don't believe it is anyway, which is called a tree. Can somebody explain a tree to me? What is a tree? You got trees outside, right? They're looking nice today, too. It's still kind of light outside. That's still weird to me. I don't know. I'm used to darkness all the time. Springtime. We got trees. We got trees in class, too. What's a tree? What's a tree? Yeah. Yeah. There you go. So I like that you compare it to a linked list. That's an interesting comparison. It does have nodes, just like a linked list has nodes, right? And those nodes are branching out. So they, there's always the first node in the list. With a tree, it has a special clever name, right? What's that called? The roots, right? So we start at the root node, that's our base node, and then that root node can go off in a couple different directions. Actually, there's no limit to how many directions, how many branches it can have. But in practice, 2 is a pretty common number of branches. You're not limited to 2, but that's a pretty common number of branches per node. And so then I can follow the left branch or the right branch and go to the next node, and that node is also going to have some branches, right? And then I can keep following, until I get to the very bottom. What do we call those? Leaves. Yeah, it's very cute, right? The one confusing part of a tree, at least in my mind, is that they're usually represented upside down, where the root's at the top and the leaves are at the bottom, unlike the normal trees where the roots are at the bottom and the leaves are at the top. You get used to it after a while, I guess. There's one particular tree that they discussed in the lecture notes for this week, and that's kind of the tree that I want to focus on. Anybody know which tree type I'm talking about? Yeah. The binary tree, right? The binary tree, binary search tree. There's lots of different kinds of trees. If you ever, don't have anything else to do in an afternoon, just Google the tree data structure on Wikipedia or something and have fun, because it's pretty amazing what you can do with trees. One of my all-time favorite data structures. I absolutely love them. Useful for all kinds of things. But let's talk about this binary tree. How does a binary tree work? I want to insert something into this binary search tree. We'll use numbers just to keep things easy, right? So I give you a number. I say, hey, put this in that tree you got over there. What's the first thing you're going to do? Where am I going to start? I'm going to start at the roots. So I look at the roots. I have my value. What am I going to do? Yeah, I'm going to compare, right? I compare the value to the roots. So you said if it's lower, you go right, and if it's larger, you go left. Really, the direction you go doesn't matter as long as you're consistent, about it, right? But for this case, we can use that. So if it's lower, go right. If it's larger, go left. So I compare the value. If it's lower, I go right. And we get to the next node, and then what are we going to do? Same thing. We're going to do the comparison again. If it's larger, we go right. If it's smaller, we go left. And then eventually what happens? We get down to the bottom, and then what do? We get down to one of the leaves, and then what do? No? I'm going to do the same thing. I'm going to compare it. I'm going to compare the value to the leaf node. If it's larger, then I'm going to create a new node on the right, and I'm going to add that value in that way. If it's smaller, I'm going to create a new node on the left, and I'm going to add that value in that way. So this tree has some interesting properties, right? It's always sorted, always. The sorting might look a little weird because it's in a tree structure with all those branches, but it's always sorted. It's always sorted. So that's how we insert something into a tree. How do we find something in a tree? We have a tree and I say, hey, go find that value 7 for me, please. What are you going to do? Same thing, basically, right? I compare against the roots. If the value I'm looking for is larger, I go to the right. If it's smaller, I go to the left. And I keep traversing down that way through each node until hopefully I eventually find what I'm looking for. If I don't find what I'm looking for, what's going to happen? How will I know that I haven't found what I want? I reach a node that is pointing to nothing, right? There's no more nodes. I reach a leaf node and I still haven't found what I'm looking for, right? There's no more nodes. Then I know that the value I'm looking for is just not in the tree. It's just not there. All right, kind of going along with our theme, what's the efficiency of putting something into the tree? Best case scenario. What's the efficiency? This was in the lecture notes too. For today. It's not constant. Not constant. I thought I heard somebody say it. It's definitely got something to do with a logarithm. I believe it's just log n. Right? Does that make sense why it's log n, log base 2 of n? Because every time I take a left branch or a right branch, what am I doing? I'm eliminating half of the nodes that I have to traverse, right? I know if I go right, I never have to touch any of the nodes that are on the left. And the same process repeats over and over again all the way down. So then finding something in the tree, since it's a very similar process, it's the same thing, right? Same efficiency. What about the worst case? What's the worst case binary tree look like? You can imagine. What's the worst case binary tree look like? It's something we're very familiar with. It looks like a straight line. It looks like a linked list. Looks like a linked list. How does that happen? That happens if I put the first value in, and then every other value gets slightly smaller, right? Or slightly larger than the last one. They're all just going to keep going in the same direction, same direction, same direction, same direction, same direction. What do I have? I have a linked list. I have a linked list out of it. There's no branches. It's just a straight line. So then what's the worst case scenario of insertion into such a ugly tree? It's a stick, right? N, right? Same thing for searching. Big O of N, worst case scenario. We're really hoping that that doesn't happen. Any questions about any of these data structures? Any questions at all? All right, let's see what I've got next. Oh, good. Let's talk about some hash functions again. I might give you a few minutes to talk to your neighbors about this one. Thinking up good ideas for hash functions. Okay, so here's a few different ideas. Hash functions for a group of people, hash functions for a parking lot full of cars, and hash functions for a set of phone numbers. So think about this. Think about what such a hash. I'm not asking you to write code. You can just describe it in English. It'll take a few minutes. It shouldn't take you too long. A few minutes, and talk to your neighbors. It's always so darn quiet whenever I let you guys work on exercises. So be loud. Talk to your neighbors. Discuss the problems. I'd love to talk to people about this. And I'll be around if you have any questions. Alrighty, excited to hear what ideas you came up with for these. So who can make a suggestion for a hash function for a group of people, group of lovely people such as people in this room right now, perhaps? What might we use as part of our hash function? Lots of potential things here. Yeah. Their name, okay, so how would we turn that into a hash function? What would we have to do to turn that into a hash function? Remember the properties of a hash function that we talked about, right? I have to be able to give you somebody's name and always get some sort of integer value, the same one, back out. So how would that work? First letter of their name, sure, absolutely. That could work. Any other ideas? Yeah. Birthday month, all right. So everybody was born in one of 12 months, so we could just use that. Absolutely. Any other suggestions? So with hash tables, the reason that I gave you these exercises, one of the things that I hope that you think about, especially when it comes to hash tables, our worst enemy with hash tables is collisions. I don't like collisions. When am I going to have more collisions, with a small hash table or a large hash table? Small, right? Small hash table equals more collisions. So what does that mean in terms of hash function? I want my hash function ideally to have a wider range of values that it can get back to me. So both of the suggestions that we have right now, letter of the first name, that's 26, right? Not bad. And then months of the year, that's 12, right? That's also not bad, but I think we can do better. What if we use a combination of the two? Sure. I like that idea. So how might that work? I look at the first letter of the name and their birth month, and what do I do with them, essentially? But how so, right? I mean, I've got two numbers. I only need one number, so I have to have some way of combining these together. What do I do? Multiply them could work. Add them. There's actually a very common operation often found in hash functions. Yeah. Yeah, you could make them into a 4-digit, so you could just stick them next to each other side by side, right? That might be pretty good, because then I could have up to, at least several thousand different combinations, I think, at that point, right? Possibly? I don't know how many combinations that would be. A lot more than 12 or 26, right? But we also want to be too careful, or we want to be a little bit careful, rather. Why don't I just say, all right, I want this hash table to have a billion addresses. Is that a good idea? That's a little overkill, right? So there's kind of a sweet spot there. We do want it to be somewhat big to reduce collisions, but we also don't want it to be massive, because I'm going to have to, that's all sitting in memory, right? That's all space that's sitting in memory, and I have to deal with those addresses, and very large addresses can be tricky to deal with. Plus, there's just a limit on the value of how large an integer can be, right? What's the limit on how large an integer can be? Anybody remember? 2 billion something. Yeah, somewhere in that ballpark, right? Hopefully you never create a hash table with 2 billion entries in it. I don't think that's a good idea, necessarily. Maybe if you got a lot of stuff that you want to put in a hash table. Like a lot of stuff. Right? But there's a relationship there between size of the hash table and how well it performs. So I like those ideas. There are plenty of others. You could use ages. That's already a number. That's pretty convenient, right? The problem is with ages, that sort of limits us in range as well. Nobody's 200 years old, not that I know of. Nobody's 200 years old, and ages will skew probably towards on the younger side, so I might have a lot of collisions in the earlier numbers and fewer in the larger values. So maybe not a best. What about like a social security number or something? What do you think about that? How many digits is that? That's, is it 9? 9 digits? That's a lot. It's not, I'm sorry? Is it 10? 10 digits? I know how to count sometimes. 9. It is 9. Yeah, it's 9. We take the dashes out and stuff, right? It's 9. So you could just use the social security number directly You're guaranteed uniqueness at that point, right? But that's pretty big. That's pretty big, yeah. Yeah, that's true. Not everybody has a social security number. I feel kind of sorry for those people, but it's true. Also, we have to be a little bit careful, depending on what we're using this hypothetical hash table for. Social security numbers change. Identity theft is, all too common these days, and when that happens, you can get reassigned a new social security number, so that could affect certain things with how the hash table works, potentially. There might be other ways, though. What if I take that social security number? Is there a way that I can take that social security number, which is 9 digits long, and somehow, shrink it a little bit, make it fewer digits, shrink the range? How might that work? I'm sorry? Hexadecimal. Oh, that's an interesting suggestion. I didn't think of that one. Interesting suggestion. But with hexadecimal, I still have the same number. Oops, it just looks different. It's still the same value, right? It just looks different. Did I see another hand back there? Modulo, yes. I've been waiting for somebody to say modulo. Thank you, sir. Modulo, you're going to see modulo in hash functions. Modulo is a great tool for us to use, because if I take the modulo of something, I'm guaranteed that whatever comes out is going to be, what? Less than whatever I took the modulus of, right? So I take somebody's social security number and I say modulo 10,000, I'm guaranteed that whatever number comes out is going to be less than 10,000. And then I can create a hash table that has 10,000 buckets, and I'm good to go, right? So I can actually dictate the size of my hash table that way if I want to. If I decide I need a bigger hash table, I just increase the modulo. Boom. Done deal, right? That's a pretty classic way of setting up one of these hash functions. Let's try another one. What about cars, vehicles? What might we use? This one might be a little trickier. I'm sorry? Could use years, right? Again, I think that's probably going to skew. You're not going to have as many older cars. The cars are going to skew newer, so you're going to have more collisions for more recent makes, for more recent years than older years, I think. License plate, sure, we could turn that license plate into a number, right, pretty easily. Even though it's got letters in it, that won't stop us from turning it into a number, right? And if we end up with numbers that are too big, then just slap a modulus on it. We're good to go. License plate's good. Any other suggestions, any other ideas? VIN number, sure. Mileage, I like that idea as well. Although, well, mileage, again, you'll skew more, you'll run out after a certain point, right? Be kind of a bell curve shape, yeah. So that's a great question. Yeah, what kind of distribution do we want? Does anybody know an answer for that? What's the ideal distribution of values in a hash table? Uniform, flat, right? Flat is better. Even if we have collisions, ideally we have an equal number of collisions across all addresses. That's an ideal case. Is that ever going to happen? Probably not very often. But that's what we want. So ideally we make it uniform. So that can influence us as well. Something like a VIN number I think would work pretty well. We could take the modulus of it. License plates I feel would also work relatively well. License plates are kind of weird because that's done on the state level, so that would change from state to state potentially. So if we're in Missouri, I could have a whole lot of values that fall within a certain range, and then a few oddballs from people who are out of town or whatever. Right, it might change, but we're getting kind of nitpicky at this point. What about the last one? A set of phone numbers? This one, maybe I should ask this one first. It's kind of a softball, right? What do we do with phone numbers? Use the phone number, sure. Just use the phone number. Take the modulus of it if you have to. Use the number. That one's easy. I should ask that one first. Any questions about this? This was fun. You guys came up with some great ideas. Some ideas I didn't even consider. That's good. Any questions? Will we try some other stuff? All right. Excellent. So let's do some coding exercise. We haven't written any code yet. I'm actually going to do this. I'm not going to do this one first. This one's actually kind of a doozy. I was thinking about this one last night, laying in bed, like, oh, that one's kind of tough. So if you're looking for a challenge, if you really want to test your understanding of linked lists, that might be a good one to try out. I was thinking through the solution in my head, and it got pretty involved pretty quickly. I want to take a look at this second one first. So I want to insert values into a linked list, but I want to ensure that after I insert that value, the linked list is going to be in sorted order, which means I have to find where that value goes, right? We can assume we're using integers in this case. In fact, to help us out here, just to kind of refresh our memory, I'm going to open up my IDE here real quick. We can use the stuff that we did last time, right? We can use the code that we did last time as a starting point. That's kind of what I had in mind for this particular exercise. So once this loads up, if you weren't here last time or you missed last time for whatever reason, you can actually find a copy of this code that I'm about to pull up on Piazza. So just go up on Piazza, look for the post that I made after class last Thursday, and grab this code and use it as a starting point. There's no reason that we need to reinvent everything that we've already done. So if you recall from last time, just to kind of review what we did, we created some linked lists, right? And we created a function that allows us to append values to linked lists. That works all well and good, but that's not what we're going for here. We're going for sorted order, right? We're going for sorted order, which means that, so append just always tacks it on the end, which is a lot simpler when you think about it. Just find the end and then tack it on. But now we want to insert potentially right in the middle. Or, I want you to also think about this, we might need to put it in the front, right? If it's smaller than anything else in the list, then we might need to put that node in the front. So let's think about what we need to get this job done, what we need to make this function happen. We can write a little pseudocode, and then I'll turn you loose on this for a few minutes so you can try it out for yourselves. So we need to start off with the function definition, right? We need to start off with the function definition. So what's the return type of such a function going to be? Any ideas? I'm not going to return void, sure. We will call it insert sorted, I guess. That'd be a good name. And then what do I need to give as inputs to this guy? Assume that we're still using integers here for the linked list. So you can kind of just look right below. This should work perfectly for our function definition. No need to make things complicated. So what do we need to do? We're going to start at the beginning of the list, right? First thing I need to do is, compare against. I want to write this in pseudocode. Compare against the first value in the list. Okay? Then what do I want to do next? What am I going to do? I compared against the first value. Let's assume that the first value is smaller than the value that I gave you. So that's not the right place to put it. Then what? What do? I have to go to the next one, right? I have to keep going. I have to keep checking. So go through all the values in the list until what? When do I know I found the spot where I need to put this value in? When do I know that I found it? Let's assume that I want small values at the front and large values at the back. And I gave you this value. I say, insert this so that the list always remains sorted. So I have to find that position. When do I know that I found it? Yeah. When the new value is larger than whatever value I'm comparing it against. So I visit each node. I say, is this value larger than this node? Or is this value larger than this node? No, it's not. So no, it's not. No, it's not. No, it's not. Yes, it is. All right, it needs to go in right there, right? It needs to be inserted right there. Does that make sense? Until we find a larger value, right? Then we need to insert the node, which is a very easy thing to say, but not as easy of a thing to accomplish. And I'll let you kind of think on that one for a while. In fact, might be a little not nice of me perhaps, but this is all the pseudocode I'm going to give to you. This is it. This is all you're going to get today. Minimal amount of pseudocode. So think about it. Talk to your neighbors. This could be a collaborative thing, a group project perhaps. I'll give you a good 5 or 10 minutes, and then we'll go through the solution, see if we can figure it out. Let me know if you have questions. How's everybody doing? Anybody think they got it? No? It's all right. This was a tough one. This was definitely a tough one. Let's work on it together. We'll figure it out. We'll figure it out together. Okay. First steps first. We're gonna compare our value against the first value in the list. That seems easy to do, right? Oh, I didn't mean to do that. I gave away part of the answer. If what? What am I really checking for? I'm checking to see if I need to add this guy on the front or not. Do I need to make this the new first node or not? Right? That's kind of what I'm asking. So how am I going to do this comparison? If what? If, well, let's be careful. We're going to assume that this is at least one thing. So that, I think we're going to make that assumption. We're going to assume that we have at least one node in this list coming in. No, yeah, there we go. If the value is less than the very first value in the list, that means that this needs to go on the front, right? That means that this needs to go on the front. Actually, I skipped a step in my pseudocode and in my regular code. What do I need to do actually very first thing? I need to create a node. Fortunately, I have the code for that. It's right down here. So I'm just going to do that. No need to redo something that I've already done. Just go ahead and create this node. All right, cool. There's my new node. Okay, so in this case, we say if the value is less than the very first value in the list, I need to add this value on the front. How do I do that? How do I add this value to the front of the list? How do I do that? Yeah. New node next equals this. There we go. That'll work. List equals new node. Okay, so what's this last piece for? So I actually think I know why you did this, and this is actually the first of a couple of tricky parts of this function. If I add a new item on the front, right, I then have a new head node, right? I have a new head node here. So I need to update my pointer to make sure that it's always pointing to the first thing in the list, right? I need to update where head is pointing, so it's always pointing to the new first thing in the list. Well, the problem is that, can I see what head is pointing to here? Or maybe a better question is, does this effectively update the head pointer to the new node of the list? Why not? What's the problem? Do I actually have the actual head pointer inside of this function? No, I have a copy of it. I have a copy of that pointer. So if I change it, it'll work fine within this function, but it won't actually change where head is pointing to overall. It won't actually change where head is pointing to overall. So how can we get around that? Can you think of how we can get around that situation? I can think of at least two ways that we can work around this. At least two ways. Anybody know one of the two? I'm sorry? Asterisk list equals asterisk new node. So what does the asterisk do? It follows the pointer and gets the value, right? It follows the pointer and gets the value. So that's going to change the actual node contents. I don't think that's going to cut it. Any other ideas? I kind of walked us off a cliff on this one on purpose. Sorry. It's kind of my job a little bit. Maybe not. I could return it. Yeah. You saw me hovering over that return type. Yeah, so do we have to worry about this with append? With append, where's the node going? Always, every time. It's going on the end every time, right? It's always going on the end. So is the first node ever going to change if we are always tacking stuff on the end? No, the first node's the same because we're just adding stuff on the end, right? In this particular case, it's possible that the node that we're inserting is going to go in the front because we want everything to remain in sorted order. That's why this problem is occurring. So one thing we can do is have a return type of a node pointer, right? Have a return type of a node pointer. That's one solution to the problem. And then so this line's not going to cut it. What do we do instead? What's our head of the list inside of this if statement? We just added new node right onto the front. So new node is the head of the list. So I can just return new node, right? I can just return the new head of the list. That changes how I call the function. We actually haven't called this function anywhere yet, right? There is another option we could have used here. Can anybody think of another way we could have solved this problem? Yeah. Make another pointer to the pointer and then pass that in, so a node pointer pointer. Yes, actually, that could work. That could work. That was not one of the two I was thinking of, but absolutely that could be a solution. So the suggestion was a node pointer pointer, and then I can change where the pointer is pointing. The pointer pointer is pointing. I don't know. Yeah. Yes, that would work. I believe that would work. That was not the one I was thinking of. Can anybody think of an alternative solution? One that you've probably seen in the CS50 coursework, perhaps. Or you might even see in Studio today or Studio last time, perhaps. Where else can I track the pointer? So the problem is I can't see this pointer. I can't see this head pointer inside of this function, right? But is there a way that I could see this head pointer inside the function? Yeah. A doubly linked list. So I could do a doubly linked list. How does that solve our problem? How does that solve our problem of updating the head pointer? Pass head in by reference. Make it a what? Make it a global variable, right? I can't see head inside of that function because head is declared inside of main, and I can't see variables inside of other functions, right? But if I declare head as a global variable, then I can see it inside of the function, right? Then I can just change head inside of the function. Boom, problem solved. I like this way actually a little bit better personally, but if you wanted to go the global variable route, by all means, that's entirely fine. We'll just have to remember that this function is going to return a node pointer to the first node in the list every single time, right? Just have to keep that in mind as we progress through. Okay, so we solved that problem. Let's move on to the next step. So this is true if we need to add the node on the front. If we don't need to add the node on the front, then we have to go through the list and figure out where it goes, right? We have to go through the list and figure out where it goes. So how am I going to do that? How am I going to traverse this list? What am I going to do? I'm going to crawl through it. I'm going to crawl through it using that same thing we did last time. We have this crawler here, right? So let's start up our crawler again. While crawler, so now, is this what we're interested in? While crawler next is not equal to null, is that what we're looking for? Maybe, actually. I mean, I guess that could work. Let's talk about maybe what needs to go inside of this loop. What are we looking for specifically? We're looking for the case, it's in our pseudocode here, right? Until we find a larger value in the list. So we find a larger value in the list. So how do I detect that? So I find a larger value in the list. Well, say that one more time for me. Well, crawler next is less than value. Crawler next is less than value. This is a step in the right direction. Crawler num is less than value. Okay, sure. Because next is a pointer to the next node in the list, right? So we keep going while crawler num is less than value. We keep going, keep going, keep going. As soon as we find that this is no longer true, hey, bingo, we found it, right? We know that this is where the node needs to go, right? Okay, so after this loop ends, then we know where the node needs to go. So the last thing that we need to accomplish is to just put that node in. We need to insert the node, right, in that spot. So what things do I need to change then? Crawler is at what position? Crawler is at the position where, right after where the node is gonna go, right? Crawler is right after where the node's gonna go. So I have to update a couple of things here. How are we gonna do this? Okay, anybody have some suggestions for me? This is another tricky part. Yes. Can I create another pointer? What for? A previous pointer, meaning pointing to previous to what? Previous to this crawler guy, you mean? I certainly could do that. Can you explain what we would use that node for? Yeah, so you're actually thinking one step ahead of me, which is, is this a singly linked list or a doubly linked list? Singly linked list. So I keep going until I find the value that's larger than me. So I have to go to the value just prior to that, right? And tell it to point to what? The new node. And then the new node is going to point where? To crawler, right? But the problem is I have no way of getting to that previous node. I've already gone past it. With a singly linked list, it's a one-way street. If I pass the thing that I need, too bad, you can't go backwards. You can't go backwards, right? So the solution to that, one possible solution to that is to create a second pointer that follows behind crawler, right? It's just previous to where crawler is. Can you envision how that might work? So how do I do that? That's actually that's also not the easiest thing in the world to accomplish here. How might I do that? I know I need another node pointer. We'll call it pre-crawler. And what is that equal to at first? Null? Okay, sure. And so then how do I update that in the list? Or I'm sorry, in the while loop. What do I set this to in the while loop? How do I change this so that it follows behind where crawler is? We can just set it to crawler, sure. We can just set it to crawler. Pre-crawler equals crawler. And then we move crawler over, right? So we just scooted them over. We just scooted them both over one, right? Scoot them over. Does that make sense? So I've already thought of like 3 different ways that we could have approached this as well. If I wanted to, I already checked the first value up here, right? So couldn't I start crawler at the second value and start pre-crawler at the first value? That would work too, right? I could start crawler at list.next, or list arrow next, and start pre-crawler at list. That would also work as a starting point. And I get there just a hair faster. But this works. I believe it'll work anyway. We'll find out in a little bit. Okay, so this is going to happen while crawler num is less than value, right? I've hit the point where I need to insert the node, so now we actually have to insert this guy. So how's that going to look? How do I put this node in? What do I need to say? What do I need to say here? So what pointers do I need to update? I've got crawler, I've got pre-crawler, and I've got new node. That's 3 nodes. What order do they need to go in when I'm done? Which node comes first in the list? Pre-crawler comes first, and then pre-crawler is pointing at new node, and then new node is pointing at crawler. So let's say that. Pre-crawler is pointing at new node. New node is pointing at crawler. Oh, wait, what am I doing? What's this? Oops, I put it in the wrong spot. I'm sorry. Why didn't any of you stop me? It has to go after the loop, not before the loop. Sorry. Oh, man, I still messed it up. I am bad at copy pasting. Okay, this is better. This is better. All right. Are we done? Yeah. Yeah, I have to return the head of the list, which, unless I change the head of the list, then the head of the list is going to be just what it was originally, right? Just what it was in the outset. Am I done? I can think of one problem. You're all going to hate me because you thought we were done with this, but no, I'm not done. What's the problem? Free. What do I need to free? I think we're actually okay on that because we took care of that last time, and that's still going to be effective for us. There's one case that could potentially cause a problem. Yeah. Well, we do need a prototype. In typical fashion, I've forgotten to do that. So yes, absolutely need that. That was not the problem that I was thinking of. Yeah, what if it's the last thing in the list? Then we have an issue. Are we doing any checking for that at all? So what's the problem here? It says, while crawler num is less than value. Well, eventually, crawler is going to do what? It's going to keep going, keep going, keep going, keep going, and potentially go off the edge. In which case, right? Crawler will become null. Does null have a num? No, null doesn't have anything. It's absence of stuff. Absence of stuff. So how do we fix this problem? This is kind of the opposite of the head problem, right? The head was at the front. Now we have a problem on the other side. How do we fix that? Yeah. Okay, I like that suggestion. Where do I do it? Get rid of the less than value. Not equal to null. So the num is not equal to null. Crawler is not equal to null. Okay, so this is not a bad suggestion, except for now we're no longer finding the appropriate stuff for the middle, right? Because if I need to stop in the middle, it's not going to find a value that's greater than me. And, yeah, there we go. I like that idea a lot. Why not both? We have both. We can have our crawler and eat it too. Sorry. So that solves part of the problem. That keeps us from flying off the end of the list, right? But we still have a problem at the end, because if crawler is null, this loop will stop, but then down here, well, actually, no, I think that'll work. Never mind, I stand corrected. I think we're cool. I think this solves that problem. Let's test it out. We've got about 5 minutes left. That should be just enough time to test it out. How about instead of these append calls up here, we use our new insert sorted instead. So I'm going to get rid of these guys. And I want to test all three conditions: inserting at the front, inserting at the end, and inserting in the middle, right? So I don't really care which way we do it, but we can say head is insert sorted. So if we want to insert at the end, I can just give it something bigger than 2, right? So 4. If I want to insert in the middle, I can give it the value in between 2 and 4, like 3. And if I want to insert in the front, then I have to give it a value that's less than 2, like 1. I'm sure I made a mistake somewhere. Yes? So which lines are we talking about here? Need to be switched? Yes? But that's what we do with the next line, right? Well, let me ask you this question. If I switch the order, does it have any effect on the overall outcome? Let's try it out. This should still be printing. Yeah, we use our print function from last time. Print list. Great. It'll even take the length of it too while we're at it. That's fun. All right. Let's try this out. I need to get to the right directory first, which is module 5 lectures, I believe. Make list practice. Did I save it? Let me just double check, make sure I saved it. Make list practice. And then run it, and hopefully I see, so I inserted values 2, 4, 3, 1. Those are not sorted. I'm hoping if we did everything properly that it will come out 1, 2, 3, 4, right? That's really what I'm hoping. And, oh, awesome. That's not a 1, 2, 3, or a 4. That's nothing. So what if we made a mistake somewhere? Let's see if we can figure it out. Do I need to check crawler equals to null first? Oh, that's a good question. Yeah. I'm checking the number of crawl before I check whether crawler is equal to null. It does go left to right when it evaluates those guys, so I should perhaps put that first, like this. Good eye. That would have taken me another 5 minutes to find, probably. Let's try it and see if that. Let's see if it works. Hey, you just saved us a bunch of time, man. Thanks. Yeah. Good stuff. It worked. It worked. I know that was a tough problem. And if I confused you, I'm kind of sorry, but kind of not sorry because confusion is how we learn things. So if this problem is still confusing to you, I will post the code. You're free to take a look at it. And I'm also happy to answer any questions you might have about this problem or any other problem. But I am, well, it's time to stop. So there is, Mike is going to start talking about bash scripting in the classroom here in just a few minutes. So if you're interested in that, make your way that way. I might head that direction myself. And remember, we do have a soft skills presentation on Thursday, and you have a studio to work on today that deals with hash maps, hash tables. So, yeah, let us know if you need any help. Thanks.